Continue on with chapter 17 that we started last time. We started talking about some electrochemistry and redox reactions. And we're sort of, again, just kind of going over some of the basics of redox here, just to make sure hopefully everybody's on the same page in terms of balancing equations and obviously oxidation numbers that we also talked about last time. A reminder that these two things always occur together. So when we have a redox reaction, that's an oxidation and reduction reaction that takes place. We talked about several definitions of these guys, but really in sort of general chemistry for oxidation, we really focus in on really the loss of electrons. And for reduction, again, it's really the gaining of electrons is really what the definitions that we focus in on. Again, people like the oil rig to remember that, or Leo the lion goes grr. Again, oxidizing is losing, reducing is gaining, losing of electrons, oxidation, gaining of electrons, reduction. Also, if you're ever sort of unsure if you can figure out the oxidation states or numbers of things, a very simple way is just to use like a number line where you got 0 and positive and negative numbers to the left of it. And as you lose electrons, which is when you go through oxidation, you lose electrons, more protons than electrons, and you will become more positive. So if you find the oxidation state moving towards the right there, that guy is going through oxidation. And obviously the opposite is true when you gain electrons through reduction. You have more electrons than necessary protons. You become more negative, and that guy is going through reduction. So you could just simply kind of move left or right there on the number line in terms of the oxidation state from reactants to products. It can very easily help you understand what is being oxidized and what is being reduced. In addition, we also talked about agents, which is the oxidizing agent. And the oxidizing agent is the substance that gets reduced. While the reducing agent is basically the opposite there of its name, and that's basically for both of these guys, it is the substance that gets oxidized. And as we talked about before and last time, the reason really the names are like that is basically what they're causing in the other substance. So the oxidizing agent is getting reduced, so it needs to gain electrons. Again, in order for it to gain electrons, it needs to make somebody else lose electrons, which means they're going to go through oxidation. While the reducing agent is something that will be oxidized, which means it will lose electrons. And if something loses electrons, somebody else has to pick up those electrons, and that would cause the reduction in the other substance. So when you're asked about the agents, either oxidizing agent or reducing agent, again, it is different than being asked what is being oxidized and what is being reduced. So make sure you keep those in your head. Also, when you're asked about all four of those things, what is being oxidized, what is being reduced, what is the oxidizing agent or reducing agent, they are all found here on the reactant side is where you find all those guys that are going through that. We finished up, I think, talking about oxidation numbers or states. And the oxidation number or state is really the charge the element would have if we sort of had a kind of complete transfer of electrons in that particular system. It should be noted, as we saw last time, that, you are sort of beat into your heads that, certain things make these sort of fixed charges, if you will, things like chlorine -1 and bromine -1 and all those kind of things. And again, that is true if it's in an ionic compound. And if it is an ionic compound, the oxidation number or state will be like the normal charges that you would have for the metal and the non-metal. Those would be the oxidation numbers. When you're dealing with something that is involving covalent bonding and sharing of electrons, or the distribution of those sharing, be it equal or unequal sharing, will give some of these elements a different oxidation state and sort of a different charge in that configuration. And you do need to sort of figure it out. So as we talked about, for example, like NaCl, that's just an ionic compound. So, the oxidation states for everybody would be their normal sort of charges. But if we took like, I just won't draw all the electrons, but We have ClO4, for example. In this configuration, we would look at the oxygens here, and we got a -2, -2, -2, and -2 for the oxidation state of oxygen. And this is ClO4 minus. And that means that we have really a -8 going on there. We do need to end up with a -1 overall. And in that particular case, that means in this configuration here, the chlorine is taking a +7 oxidation state. Here it's sharing electrons with all those oxygens. And based on electronegativity, oxygen is probably a little bit more electronegative. So we're going to pull those electrons a little bit further towards each of those oxygens, making the chlorine more and more sort of electron deficient, which is why in this particular arrangement, it is going to sort of achieve a positive oxidation state. And that's different where in the ionic compound, we got that complete transfer of electrons from the sodium to the chlorine. So the chlorine picks up a complete electron and becomes more negative in that case. So sometimes people have a really hard time with oxidation states in that sense. Like I've learned this is the charge and it cannot be anything different than that. The other important things that we also talked about when talking about giving oxidation numbers or states is you do need to give the charges. So if it is +1, you do need to write the plus and the 1. If it's negative, you do need to put the negative signs in there. And also in a situation such as this, sometimes people will go, oh, there's 4 of them. So the oxidation state of oxygen there is -8, and you don't want to do that. You want to give it for each individual one. And obviously each individual one in that particular example there would be -2. Any questions on any of that stuff there? Okay. We talked about sort of writing half reactions as well. And half reactions, there's an oxidation and a reduction, a half reaction. We know it is the oxidation half reaction because we do see the electrons on the product side, like they're being given off. We also know that it is a reduction half reaction when we see electrons on the reactant side, like they are being gained. They're called half reactions because when you add them back together, obviously the electrons should completely cancel out. So in a simple sort of redox reaction, if you have the half reactions, you want to make sure obviously that in each half reaction, you have the same number of electrons because whatever electrons somebody loses should be the electrons that somebody gains. And in a case where you don't have the same number of electrons, you may have to multiply one half reaction by a number or maybe both half reactions by a number to get those electrons to be the same. When you add them together, electrons will completely cancel out and you'll be left with the overall reaction that is taking place. So in a simple sort of redox reaction, that's really the only thing of concern is just simply just make sure you got the same number of electrons before you add them together. Anything on opposite sides of the arrow can cancel or reduce down. Now there's a little bit more difficult sort of balancing of redox reactions which occur in acidic or basic solution. They require a few more steps along the way when you do this. So we'll take a look at this one and go through it again just to make sure everybody hopefully is on the same page. Again, you might have learned this in 50 or maybe not. So if not, I guess you'll learn it right now. When we have acidic or basic solutions, and we'll start with acidic right now, and we have a redox reaction such as this, and we want to balance it. There's a few things that you want to do. Maybe the first thing is a good idea is to sort of figure out what is being oxidized and what is being reduced in this particular case. So let's start with the iron. The iron is being oxidized or reduced here. The iron in this case is being oxidized. You can look at the oxidation state here, which is +2 and +3 over here for the iron. So if you just went to the number line there, +2 is like there, heading to +3, going to the right, which means it is going through oxidation. By default, that means that this guy right here is actually going through reduction, but we can figure that out as well. Oxidation, the dichromate here for the chromium is +6. I think we did it on the last example there, previous. By the way, that's -2 for the oxygen, gives you -14. We need a -2 left over, and there's 2 of them, gives you a +12. Chromium over here is +3. So the chromium is starting at like +6 and heading towards +3, which means it's going in the negative direction, which means it is going through reduction. So again, the nice thing as well is if you can figure out one, you obviously know what the other guy is doing. That means my reducing agent is which one? My reducing agent is this guy. Reducing agent, right, is a guy going through oxidation, and my oxidizing agent would actually be the chromium there. Chromium with a +6 charge would be my oxidation agent, oxidizing agent. All right, so now that we sort of have everything figured out, which is sort of helpful to know, the first thing you really want to do when you have a sort of problem like this is you just want to separate out the reaction there into the two half reactions. One would be an oxidation half reaction, one would be a reduction half reaction. The simplest way to do that is basically just take the things that look like the same element, try to put them together in a reaction. So if we did that here, obviously we have iron going to iron 3. Obviously the two irons together, and the two chromiums would also go together here. So our dichromate to our chromium 3. Since we did a little work ahead of time here, we already know that this is our oxidation half reaction, right? And this is our reduction half reaction there on the bottom. The first thing you want to do after you split it off into the half reactions is you want to balance, except for hydrogen and oxygen. So you would balance them like you normally would balance an equation, and you would use a coefficient. In the case of iron, there's one iron on each side. They have different charges, but there's just one iron. In the case of the chromium, we do need to actually put a coefficient in front of there, and we will go with a 2 to balance that guy out. Now, once we've balanced every element besides oxygen, hydrogen, we then will balance the oxygen. So we're going to balance the oxygen by adding water. So you're going to add water to whichever side needs oxygen. And the deal, though, is once we add water, we're not just adding oxygen, right? The other part of water is hydrogen. So you need to add water to one side and then 2 H pluses to the other side for each water that you add. And that is because if you don't add the H pluses to the other side, you will be short hydrogen when it's all said and done. So we sort of add H plus for hydrogen. So water to the side needs the oxygen, 2 H pluses for every water you add to the other side to make sure we have the same number of hydrogens. By the way, if you ever start out with an unequal amount of hydrogen on one side or the other, you could just add H plus to whichever side needs the hydrogen. That way you can kind of balance it out up front. So we're going to do that now. When we look at the iron half reaction, there is no oxygen on either side, so we don't need to add water. When we look at the chromium one, there's 7 oxygens on the left and none on the right, which means I'm going to add 7 waters to the right-hand side. Because I added 7 waters to the right-hand side, that means I need to lay up here 14 H pluses to the left-hand side, again, to balance out the hydrogens that I've added. Questions on that so far? Okay, so now that we balance all the other elements and we balance the oxygen and the hydrogens, really kind of the last thing that we want to do is we want to add electrons to balance out the charge on each side. Now the charge on each side does not need to equal 0, it just needs to equal the same charge on each side. And clearly the only thing we're adding are negatively charged electrons, so whichever side needs the negative electrons. Looking in the top one, I got a +2 on the left and a +3 over here, which means the top one will need 1 electron on the right-hand side. That 1 electron gives me a +2 on the right and a +2 on the left. When we look at the bottom one, and by the way, I'm just looking at overall charges on left and right, because why reinvent? Well, that's what to take into account is everybody's individual oxidation number. So no sense going individually through each element here. So this is a +14. That is a -2. That is a grand total of plus 12 on the left. On the right-hand side, that is plus 6, and 0 gives me a plus 6. That means the left-hand side here will need 6 electrons added. That gives me a plus 6 on the left and a plus 6 on the right. Any questions on that so far? Yeah, is those neutral? There is oxidation numbers for each of them, but remember that when you add up all the oxidation numbers, it equals the overall charge on the molecule. So if its charge is 0, all those guys just 0 out anyway, so no need going individually through it. And obviously, like the dichromate, there's a lot of oxidation numbers like plus 6, minus 2 going on there, but they all add up to minus 2 overall. So it's just easier to take the overall one. Other questions? All right. Now, since we also earlier determined half reaction, which one's our reduction half reaction, we can make sure we didn't screw up. This is our oxidation half reaction, and I do see electrons on the right-hand side, which is where they should be. The bottom one is the reduction half reactions, and I see electrons on the left-hand side, which is where they should be as well. If you ever add electrons to the same side of the equation, frankly, you screwed up. Yes, and you should go back and fix that. They should never be to the same side of the arrow. They always should be opposite. Now, we're ready to, at this point, once we add our electrons, really add back each half reaction together. But obviously, the simple thing that we talked about before is we need to make sure that we have the same number of electrons in each. And clearly there we got 1 in the top one and 6 in the bottom one. So this will require us to take the top guy and multiply the entire thing by 6 to give us the same number of electrons. And what I'm going to do is just kind of erase some of my scribble there so I could go underneath it, I think. There we go. So rewriting the top equation and multiplying it by 6 underneath here gives me 6 of the iron 2 goes to 6 of the iron 3 plus 6 electrons. I now can add both of those reactions together. Anything on opposite sides of the arrow can cancel or reduce. The electrons should always 100% cancel each other out, which they do here. I think that is it in terms of canceling. So that is going to leave us a 14H plus on the left, plus a Cr2O7 2 minus, plus a 6 of the iron 2. So that's everything on the left-hand side of the arrow stays there. Everybody on the right-hand side of the arrow will stay as well. 2Cr3 plus 7 waters, plus 6 of these guys here. And if I did not screw this up, it's a good chance. It should be balanced really 2 ways. It should be balanced like a normal reaction or equation where you have the same number of elements on both sides. So if we look, we got 14 hydrogens on the left and the right, 2 chromiums. We have 7 oxygens left and right, and 6 irons on the left and right. And it should also be balanced. Overall charge on the left should be the exact same charge we have on the right. Overall charge on the left is plus 14, minus 2 is plus 12, plus 12 and plus 12 is a plus 24 on the left-hand side. Right-hand side is plus 6 for the first guy, and plus 18, which gives you a plus 24 on the right-hand side. So this would represent the balanced redox reaction in acidic solution. Any questions on any of those steps there? Yeah. Now, let's talk about what happens for basic solution. If this happened to be basic solution, my recommendation is to just do what we just did and balance it in acidic solution. And once you balance it in acidic solution, you could then turn it into the basic equation by adding OH minus to both sides. So let's take a look at what we would do. And it's probably the simplest way to do that. Let me just recopy this. 14 H pluses plus Cr2O7 2 minus, 6 of the Fe2 plus. On the other side, 6 of the Fe3 plus, plus what we got there, got 2 of the Cr3 plus. And we have 7 waters. Redox. All right. All right, so this is our equation here in acidic. And if you had to balance this guy in basic, again, I would just do exactly what we just did in basic conditions. The difference is here, what we're going to do to kind of turn it basic is we're going to add OH minus to both sides. And the amount of OH minus we're going to add is going to be equal to the amount of H plus that we have there. So on the left-hand side, we have 14 H pluses, which means we're going to add 14 OH minuses to both sides here. Now, when you do this to the side where we have OH minus and H plus, OH minus and H plus will make a little bit of H2O. Yeah, so that will make some H2O. And what will typically happen at this point is you will have some H2O that you need to cancel. So if we look here, we have 7 H2Os on the right. That will reduce this guy down to 7 waters. And at this point, that would give us 7 H2Os plus Cr2O7 2 minus plus 6 of those guys goes to 6 of these guys plus 2 of those and 14 of those. And if I did this correctly, this should now be the same equation balanced in basic conditions. Should still have the same number of elements on both sides. So 14 hydrogens, 14 oxygens, 2 chromiums, and 6 irons. Overall charge on the left-hand side is plus 12 and minus 2 is plus 10. Overall charge on the right-hand side is plus 18 and 6 is 24. So it's plus 24 and minus 14 is plus 10 on the right-hand side. So it again is balanced both ways. Question on that there. We've done this before, yes or no? Ish. Okay. By the way, we know the bottom equation there is a basic equation. Why? Yeah, because it has OH minus. Just like on the previous one, we knew it was balanced in acidic conditions because it ended with H plus. Yeah. So if you see one of these guys balanced and you're doing in acidic or basic conditions, you definitely should end up with H plus on the side or OH minus on one side there. Any questions on any of those steps? All right, well, I did one. Now I think you should do one. I'll scroll the much prettier version of this here through the screen in case you want to watch it, you know, while you're re-watching the videos to put yourself to sleep. You know, it's good. And hopefully they got the same answer as us. That would be good too, I suppose. All right. All right, so why don't you give this one a go here. Starting with this guy, we're going to balance it in basic conditions. So balance it in basic conditions. Also, why don't you identify ID the oxidation and reduction guys and the oxidizing agent and reducing agent. All right, take a few minutes. Okay, let's take a look to see how you're doing. So you can just start with splitting it off into really the 2 things that kind of go together. So I minus and I2, and then obviously here a little permanganate, which we will see on Thursday, and a little MnO2, which we will also see on Thursday, I think, as well. Again, here we can sort of figure out what is going on. So if you want to do just a little number line action here, that is a -1, obviously, for our iodide, and that is a 0 there for our I2. So the I is going from -1 to 0, which means it's going in the positive direction, and it is going through oxidation. While by default, obviously, the guy on the bottom there would be going through our reduction, but let's see how we got there. Oxygen's -2, that's -8, leaving a -1 left over. would give the Mn on this side a +7 in this case. Going on the other side, -2 for the oxygen, -4 gives us a +4 to get us to 0. So in terms of the Mn, it is starting at +7, which is like here, and ending at +4, which is heading in that direction, which means obviously it is going through reduction. That means that the I- would be my oxidizing agent or reducing agent. Yeah, my I- here would be the reducing agent, and my MnO4 minus, or really my Mn7 plus there, would be my oxidizing agent in this case. Yeah. Any questions on that there? Okay, so now we got that all sort of sorted out. And get rid of the oxidation states there just to kind of clean it up a little bit here. Boom and boom. Okay, we're going to go into our steps here where we will then balance everything outside of oxygen and hydrogen. In this case, looks like we do need to lay up a 2 there for the I. We have 1 Mn on each side, so we're good in terms of that. Next, we can now proceed to oxygen, and in this case, there is no oxygen in the top one. Bottom one has 4 on the left and 2 on the right, which means that the guy on the bottom there will need 2 waters on the right-hand side. Because we added 2 waters, that means to the left-hand side there, that is going to give us 4 H pluses. At this point, we have pretty much balanced everything. So what is left to do is balance out the charge by adding our electrons. And in the top, we have -2 on the left, 0 on the right overall charge, which means the top guy does need 2 electrons to balance it out. That also does agree with our oxidation rates. It's on the correct side. Bottom guy, that is +4 here and -1 here. That's a grand total of +3. There is no charge on the other side, which is 0. That means that we do need 3 electrons and that guy there to balance it out. Any questions on adding the electrons? Okay. So now we're to the part where we are ready to add everybody back together. But once again, we can't do that until we do have the correct number of electrons in each half reaction. Common number between 2 and 3 is 6. So we do, in this case, actually need to multiply the top reaction by 3. The bottom reaction needs to be multiplied by 2. That way we will end up with 6 electrons in each of the half reactions. So just recopying it and multiplying those guys underneath will give us up on top 6I- goes to 3I2 plus 6 electrons. Multiplying the 2 across the bottom there gives us 6 electrons plus 8 H pluses plus 2 of the MnO4 minus and 2 of the MnO2 plus 4 of the water. At this point, we are free to add these guys back together. Our goal here of canceling out our electrons works. And we end up with, again, everybody on the left-hand side stays on the left-hand side. So that is 8 H pluses plus 2 MnO4 minus plus 6I minus. Right-hand side, 3I2 plus 2 MnO2 plus 4 waters. And if I was balancing this in acidic conditions, I would put a box around it and I would be done. This would technically, again, be balanced in acidic as we see the H pluses there on the left-hand side. But in this case, we did want basic. So we need to do the additional step here of adding OH minus to both sides. Once again, equal to the number of H pluses that are there. And let's see here. I feel like I mismultiplied somewhere. Hang on a sec here. 6, 2, 2, 2, 4. That looks good. There we go. So that's That's 0. I just can't add. That's good. Plus 8 and minus 6. That's 0. So it looks good. All right. So we're going to add our 8 OH minuses to both sides because, once again, here we do have 8 of these H pluses. That is going to give us 8 H2Os over here on the left, which can then be reduced down to 4 H2Os by just subtracting from the other side. That gives me 4 H2O on the left, plus 2 of these guys, plus 6. Gives me 3I2 plus 2 MnO2 and 8 OH minus. And this should be our balanced equation in basic conditions. We got 8 hydrogens on the left, 8 on the right. We got like 12 oxygens on the left and 12 on the right, 2 MNs on both sides and 6 I's on both sides. Overall charge on the left-hand side is -8. Overall charge on the right-hand side is -8 as well. So we are balanced in both ways there. Any questions on that there? I personally think this is the easiest way to balance it in basic conditions. Some people, like I was taught years ago, would be to add the OH minuses before you add the electrons, which you absolutely could do, except there's a lot more sort of waters and canceling things out and stuff like that. So it gets a little bit more cluttered if you kind of do it earlier. It's much more cleaner and easier just to do it at the end. So you can just balance everybody in acidic conditions and then flip it over. Any questions on how to balance these equations? Do you need to know how to do them and responsible to know them? Stuff. All right. So there's a couple more on the page there, or the notes. If you want to practice, you can. So we'll just skip ahead since everybody seems confident in doing those, I hope. Then let's talk about really sort of the main focus of this chapter, which is galvanic cells. Galvanic cells are really redox reactions that occur. And this is sort of a traditional galvanic cell that you could build in a laboratory. So you got a couple of beakers. We have some solid electrodes here. And typically in the beaker floating around is the aqueous version of basically those solid electrodes. So on the left-hand side, we have a zinc electrode, and we got some zinc 2 ions floating around in the solution. Right-hand side, we got copper, and the copper 2 ions floating around in the solution. On one side of the galvanic cell is where oxidation occurs, and that is what is known as the anode. So in the anode compartment, oxidation occurs, which means electrons are lost. Typically, these guys are connected by a wire. So the electrons basically travel from the anode, gives you some voltage, across the wire to the other side, which is our cathode side. And the cathode side of a galvanic cell is where reduction takes place. So in the super zoomed picture on each side, we see what is happening as a result of these electrons moving. On the anode side, when the electrons go away, basically the solid zinc goes for a swim and becomes zinc with a +2 charge at that point. As those electrons travel to the other side and the cathode side and come in, they find some aqueous copper in this example, which then actually jumps out of solution and becomes solid at that point. So sort of plating on that case. The electrons is very similar to sort of, what we use a battery for. They go out through the device, they can power everything, and this redox reaction could be used to do some type of work. Now, what you usually need when you do a galvanic cell is this little piece right here, which is quite important in a sense. It is a salt bridge. The salt bridge has some type of ionic compound in it. In this particular case, is potassium chloride. I think when we get to that experiment, we use like potassium nitrate, but some type of ionic compound basically is going to be there. And what ends up happening is the ions from the salt bridge actually kind of flow into one beaker or the other. And in this case, you can see that the negatively charged ion is flowing to the guy on the right, while the positively charged ion is sort of flowing into the guy on the left. The function of the salt bridge is to keep really everything flowing, basically. And in general, you could think of the cathode side as being more positive, if you will, and that's very helpful because that's going to draw those negatively charged electrons across the wire to the other side. So you may be asking, does it matter if we have the salt bridge? If we take the salt bridge out, what would happen? Well, let's just say, for example, we did not have the salt bridge there and we took it out. And the result of that would be what is essentially happening as this cell is running is these zincs are jumping out into solution and coming into solution as a positively charged ion, which means if you did not have the salt bridge, what you would essentially do is build up a bunch of positive charge on the left-hand side there in your anode compartment. What's happening on the other side? Well, the electrons are coming in, the positive guy is jumping out of solution, which means you're left on the right-hand side with a bunch of negative ions building up if you did not have the salt bridge there. Now, why would that be bad for electrons trying to move to the other side? Electrons are negatively charged, right? Opposites attract, which means if you don't have that salt bridge and you build up this giant positive side over here, are the electrons going to want to leave? They're not going to want to leave. In addition, they're definitely not going to want to go to the side that is now more negative, right? Like charges repel each other. So without the salt bridge there, you'll get this buildup of the charges on the wrong sides. And what that will essentially happen is you will cease to flow electrons at that point, and your cell will not work so well. So with the salt bridge present, this is why when we look on the left-hand side, we see the negative charge ion flowing in there, because what that's going to do is now cut down on the positive buildup that we get on the left-hand side. And our positive ion from the salt bridge going to the right-hand side, which will also cut down on the buildup of the negative charge on that side. Thus, we can sort of maintain our kind of natural positive charge, a little bit more positive on the right-hand side to keep those electrons flowing from one side to the next. So the salt bridge, really functions to prevent the buildup of the wrong charges, allowing sort of the right combination of more positive on the cathode side to allow those electrons basically to get to the other side. Any questions on that there? So we can look at our half reactions here, and our zinc is being oxidized, as we can see down here, the zinc losing a couple electrons, the copper gaining the same electrons. It is still a redox reaction where whatever electrons is lost on the anode side will be gained on the cathode side. Writing our reaction together gives us the overall reaction that is happening there. Zinc is going from 0 to +2, which is being oxidized. Copper is going from +2 to 0, which is being reduced. Any questions on a galvanic cell, what it looks like? You obviously need to know, the setup of a galvanic cell. So here's actually that cell, I think actually together there with a voltage meter there. And you can see you got some positive voltage happening there, which is really good. There's our solid electrodes. Really hard to see, but there is a salt bridge right about there that's connecting those two together. And again, in this case, that electrical potential difference between the anode and the cathode side is called the cell voltage. A volt is 1 joule over a coulomb, which is a C. It's also called EMF, electromotive force, or cell potential. And again, it really is that sort of a little bit more positive on the cathode side, which is going to pull those electrons to the other side. So sometimes in problems, you're asked to calculate the cell voltage, you're asked to calculate the EMF or the cell potential. Pretty much if you're asked any of those things, they really just want you to calculate the cell voltage in most cases is what they're really asking you to calculate. Here's our overall reaction as we just saw. We can also write a cell diagram, which is this guy down here. And it's sort of a shorthand for a galvanic cell or a reaction like this. And it is always anode first, followed by the cathode. So this is sort of the anode compartment, the two parts, and the cathode compartment. These two lines here represent the salt bridge. Now, sometimes you are given the cell diagram and you need to kind of put it into an equation. And the simple sort of formula of how cell diagrams go is pretty much like this. First guy is a reactant, second guy is a product. Reactant, product. So you can see here, zinc is a reactant. Zinc with a +2 is a product. Zinc with a copper 2 is a reactant. And copper with no charge is a product. So that's the general way you can kind of go from a cell diagram back to the equation. Occasionally, they will put other things in the cell diagram. So here we have molarity, which is 1 molar. Sometimes they won't if it's standard concentration. They typically will if it's not standard 1 molar. Or sometimes there will be gases involved in these sort of reactions. So things like hydrogen, which does not have a sort of solid form, they'll use something like platinum or some type of metal like that as the physical electrode, and you'll have gases involved in there. So sometimes you'll see pressures in here as well for those type of situations. Any questions on cell diagram there? So when we deal with galvanic cells, we typically deal with a certain type of value that we use a lot, and that is what is known as the standard reduction potential. Is sometimes abbreviated as an SRP for standard reduction potential. They are standard reduction potentials, which means they are reactions that are basically written as redox, not redox, the reduction reactions in this case. So if we hook up this particular cell here, zinc with the hydrogen electrode, and as you can see, hydrogen is the electrode here. It is a gas. So in this particular case, they are using something like platinum as sort of the physical electrode in this case. And what we see here is the zinc is going through oxidation again. So once again, here our zinc is going to go for a swim into here as zinc +2. Electrons will travel from our anode to our cathode, coming down into here and finding our H+ that's in the solution because there's hydrochloric acid. These guys will then go through reduction and form H2, which is really the bubbles that you're kind of seeing there form. And that is going through reduction. Our overall reaction here is our zinc plus our 2 H+ going to our zinc with a +2 and our hydrogen there, which has an oxidation state of 0. And again, we're sometimes we'll see some pressures sort of indicated in here as well, since we're dealing with pressures. So much like in a lot of areas of chemistry, when we can't necessarily sort of directly measure something, a lot of times what they will do is sort of come up with a standard to use to compare everybody to. And what they use for standard reduction potentials or SRP values is a hydrogen electrode, which is sometimes referred to as the standard hydrogen electrode, or the SHE for standard hydrogen electrode. And they basically assigned it a SRP value of 0. So they basically assign hydrogen here an SRP value of 0, and that is what this value represents. And this is our reduction reaction. Again, we see our electrons on the left and our H+ there being reduced by gaining those electrons. Now, they use the standard reduction, standard hydrogen electrode to figure out the SRP values for everything. And there's a big table we will see in just a second of SRP values. And as we will talk about, since these are really redox reactions, there is a oxidation reaction occurring and a reduction reaction occurring, which means when we go to the table and find the two things involved in a galvanic cell, really only one of the reactions that we see in that table is correct, as they are both written as reduction reactions. The good news is the oxidation reaction is simply just turn the reaction around, basically, and you will have your oxidation reaction. So we do need to flip typically if you want to write a balanced equation that's going on one of the reactions that you see in the table. Otherwise, again, your electrons will be on the same side. And we'll talk about what you do with the values and stuff like that in just a second. So they take something like the standard hydrogen electrode and basically hook it up with a whole bunch of combinations of elements. And by doing so, they can calculate the SRP value for all the elements that we do see on this table. So in this particular case, the one that we just did, if they hooked it up there, they would have got a cell voltage of 0.76. And using this equation right here, E of the cell is equal to E of the cathode minus E of the anode. We can figure out the cell potential there really for our anode in this particular case. And that will give us that the zinc is actually minus 0.76 volts would be the SRP value and what you would find in the table for zinc. Again, it's a reduction reaction here. This is an important equation, and I'm going to tell you something about this equation right now, which may make sense or may not make sense yet, but hopefully eventually will. Now, as I just mentioned, technically speaking, when we will go to this SRP table and we grab the two values, technically one of the values are incorrect because it should be an oxidation reaction, not a reduction reaction. So if you don't want to mess around with changing the sign of what you find in the table to make the oxidation one the correct value, you should use this equation and subtract. Now, if you want to be correct and change the sign on the oxidation half reaction, which is basically all you do when you reverse the reaction, is just change the sign, what you find in the table, you should add those values together. You should take the E of the cathode plus the E of the anode if you change the sign. Now, if you leave the sign alone, you should use the one where you subtract. And the reason for that is why you are subtracting here, because it will change the sign of the anode, which is the oxidation one, which is always the one you need. So for example, let's just say that we took this guy right here, and this obviously we'll say this is our cathode. And we'll take our hydrogen there, which will be our anode. And our hydrogen here. And we'll just use our 0 here. Maybe it's not the best example here, will be our anode. All right, so technically speaking, in this particular case, actually we'll do it backwards. We'll do it this way, that we're flipping the other one. This will be our cathode, and we'll do this guy as our anode. All right, so we'll do it just like we see up here. All right, so if this is our anode and this is our cathode, what we would want to do, they're both technically written as reduction reactions. This is how we would find them in the table. We would calculate E of the cell by taking our cathode, which is 0, minus our anode, which is minus 0.76 volts, will give us plus 0.76 volts, which is our cell voltage that we have going on here. Now, if you look at this and go, well, I want to be absolutely correct in the way I do things, which is good, you would want to actually reverse this reaction, because this is not a oxidation reaction, this is a reduction reaction. And what you would do is, if you decided yourself, I want to reverse this reaction, this would then give me zinc that goes to zinc 2 plus 2 electrons, which is the oxidation reaction. And what happens when you reverse the reaction is the sign of this changes. So this would technically plus 0.76 volts. And when you write a reaction, it should have the correct E value with it, which in this case would be plus 0.76 volts. Because I chose to change the sign, I would want to use this equation up here and go, my cathode is 0 and my anode is plus 0.76 volts. Gives me 0.76 volts, which is positive, which is again what we want. You don't want to change the sign and then subtract, because then it will basically unchange your sign for you and you end up with a negative value here. So technically speaking, one of the reactions when you're doing a galvanic cell and you go to that table should frankly be reversed, and the E value that you find in there should be changed the sign. So if it's positive, it should become negative. If it's negative, it should become positive. So if you want to do that, that's perfectly fine to do. Just add those numbers together after you change the sign. If you don't want to worry about changing the sign, just take the numbers exactly how you find them in the table and subtract the cathode from the anode, and the negative there, or the subtraction, will change the sign for you. I recommend you basically choose one method and stick with it, so you're not like changing the sign then subtracting by accident or something like that. So decide if you want to change the sign and then add them, or not change the sign and subtract them, and again, you'll be in good shape on that. Any questions on that there? Okay. So if we hook up this standard hydrogen electrode here with copper in this particular case, we see here that in this case, it is our hydrogen that is our anode, and our copper here is our cathode, and that gives us a positive 0.34 volts. Applying the same sort of math as what we did before there, this will give us an SRP value for copper of plus 0.34 volts. This also demonstrates a couple things. In the previous example, the hydrogen electrode was the cathode. In this example, the hydrogen electrode is the anode. So anything can be an anode or a cathode. Just depends on whether or not it will work for you. What it means to work would be positive voltage is good, negative voltage not so good. The good news about galvanic cell is if you get negative voltage, you just switch them around, right? Your anode becomes your cathode, cathode becomes your anode, and you will turn it into a positive voltage in that particular case. Just like a battery, if you put it in backwards, basically, right? It doesn't work right until you flip it around the right way to get the electrons flowing in the correct direction. So here is an example of an SRP table. You have a similar one in your book that goes on for pages like this one. Obviously, this would be provided for you. But once again, if you look on this table, everything is written as a reduction reaction. So once again, if we wanted to write the oxidation for this guy, we would simply just flip it around, and it would go from cadmium to cadmium 2+ plus 2 electrons. The SRP value would then become positive 0.4 volts. And again, you could do that for anybody here. And if I did that once again, I would want to use the equation and add it since I changed the sign, or you could leave it as -4 there, 0.4, and subtract. Here's a number table, which clearly you can see all the values on that table. A couple of things about these SRP values that you would find in a table. It is the SRP value that you see is technically written for exactly how the equation is up there. So if it's changed, you do need to reverse the sign that you see there. Now, if you're not given any information about the reaction that's taking place, and you just simply have a question which says, hey, you built the galvanic cell out of these two things, how do you know what is going to be your anode or what's going to be your cathode? You could use the SRP values to help you decide that. If you're not given any information about what's going on in the reaction, and you're just given these two things make up the cell, you could look at the SRP value, and the one that is more positive will have a greater tendency to be reduced. So if it has a greater tendency to be reduced, would it be your anode or your cathode? Reduction happens where? Happens at the cathode side, yeah. So if you're not given the reaction or any information about how it's occurring, you could use the SRP values, and whichever one is more positive will be your cathode, and by default, the other guy would be your anode in that particular case. By the way, if you are given information about how the reaction is taking place, or you're actually given a reaction, you should look at the reaction and see what is being oxidized, what is being reduced, and that will tell you what is your anode or your cathode in that particular case. But if you're not given any equation, more positive will be your cathode. As I mentioned before, we can reverse one of these reactions, and you simply just change the sign of E. As we saw earlier, occasionally you will need to multiply a half reaction, or maybe both of them, by a common number to balance the equation. It actually does not affect the value of E that you see in that table. So if you need to multiply it by 6 to get the right number of electrons, you would not multiply the E value by 6. You would just leave it alone. So that's one kind of slightly different thing. All right, so why don't you give it a try here? What is the voltage here in this cell? Also, why don't you write the balanced equation here? These would also obviously be SRP values you would find from a table. So first off, we're making a galvanic cell here. So which one should be our cathode? In this case, we could look at the SRP values, and the one that's more positive is this guy. Yeah, that would be more positive. That would be our cathode. That would be our anode. So if we wanted to obviously just calculate E of the cell, we could take our cathode minus our anode. And in this case, would give us minus 0.4 volts minus a minus 0.74 volts. Going to get us a 3.4, I think. A 0.34 volt for our E of the cell. Any questions on that part of the calculation? Since this is our cathode, it is okay the way it is, since we want to write the balanced equation. Our anode does need to be reversed, and we also need to make sure we have the same number of electrons, which we don't, so we do need to multiply the top guy by 3, bottom guy here by 2. So I'm going to do that. I could just stay the same. So 3 of the cadmiums plus 6 of the electrons gives me 3 of the cadmium. By the way, by multiplying that by 3, it has no effect on this value. We're going to multiply the bottom guy by 2 and also reverse it as well, just to save a step here. So that's going to give me 2Cr, 2Cr, 3 plus, and 6 electrons. Once again, here, multiplying by 2 has no effect, but the reversing does. It does change this guy to a positive 0.74 volts in this case. Adding both of these back together, our electrons cancel, which is what we're looking for. Gives us 3 of the cadmium with a +2 charge, 2 of the chromium with no charge, go to 3 of the cadmium with no charge, and 2 of the chromium with a +3 charge. So this would be our overall reaction in this case. Any questions on that? And it is balanced like we talked about before, 3 cadmiums on both sides, 2 chromiums. Overall charge on the left +6, overall charge on the right +6 as well. Now, if you chose to do it this way, where you can see I changed the sign here, and you wanted to calculate E of the cell, you would then add these together because you already did the changing of the sign, and will give you a positive 0.34 volts. So again, because you changed the sign, you want to add. In that case, if you did it that way, or as you can see, you could just simply go to the table and just subtract, and you're good to go that way as well. So you could do it either way. Any questions on any of that there? Okay. Let's take one more here to finish it out. Galvanic cell made of magnesium and silver. Why don't we just calculate the voltage here for this particular one? And once again, this would be the values you could get from the table here. And we do see that this guy is more positive, which means that should be our cathode. By default, obviously, this guy would be our anode. And since we're just going to calculate the cell voltage here, we're going to take the cathode minus the anode. So since I'm going to subtract, I'm not going to change any signs. So we would take our 0.8 volts minus our minus 2.37 volts. And that will get us 0.8 plus 2.37. a positive 3.17 volts, as we'll talk about. That is good, a positive voltage in this case. Any questions on that? Again, if we were looking to balance it, the overall reaction, we would need to multiply this top guy by 2, and we could leave it exactly the way it is since it is the cathode reaction there. The bottom one would just need to be reversed as we have 2 electrons in that, and that would give us Mg2 plus 2 electrons, which technically speaking would then reverse the sign of that guy to 2.37 volts. Here our electrons would cancel, giving us the overall balanced equation of what is happening here. And once again, if you chose to change the sign, which is perfectly fine, at this point, we would want to add those two together. So we're going to add those two together and gives us the 3.17 volts. Any questions on this here? All right, we will lay it up there for today.